Okay, so am I supposed to start or will
Yeah, you can share and start whenever you like.
Okay.
If you share, I'll have a refresher on what the title is and I can introduce you.
Okay, perfect. Wait a moment, I have to but it's wait a moment. Okay. Okay. So do you see well or not so well? Okay, it seems now it's okay.
I'm actually so happy you're doing it like this.
Okay.
Yeah, this is super cool. Okay.
Yes, I'm sorry, just that it's moving a bit the focus. I hope it stabilizes.
It seems pretty stable.
It looks pretty good right now. So
okay, perfect.
We're very happy to have Matteo Viale, who's going to talk about the absolute model companionship spectrum and the continuum problem.
Okay, well, I'm very happy to have the occasion to talk in your seminar. And actually, this is a follow-up of a seminar I gave 2 years ago when I started to have this type of results. But there I still had them in a very preliminary form, and now I have a very, I think, clean organization of the results. And essentially, those results amount to present using model theoretic terminology and ideas, many generic absoluteness results that were obtained by various people, starting with the seminal work of Woodin on generic absoluteness results for second order arithmetic, then the PMAX work, which gets generic absoluteness results for the theory of H-2, and then the combination of these results with the bounded forcing axiom results, and so on and so forth. And I will show that we can use the notion of model companionship to give a very neat model theoretic presentation of these results, these generic absoluteness results. Okay, so let me start from the beginning with, so essentially this will be a basic model theory talk for almost all of the time. And in the last part, I will present essentially a way to classify first order theory using the notion of model companionship. And then I will apply these classification tools that I'm going to introduce to use them to analyze set theory as axiomatized by ZFC, and see what this model theoretic tool says about set theory and how many generic absoluteness results can be rephrased in this model theoretic terminology. So let me start with the following basic fact. Let TS be tau theories. Oh, that's terrible. I don't understand why. Let's see.
It's okay. Maybe it just needed some letters to focus on. It seems to be clearing up.
Okay. The problem is when I'm moving. Okay, no, that no. So the problem is when I move. It seems that it shifts the focus. The following are equivalent. One, T, I'm very picky and I'm extremely redundant in notation, but because we will soon see that this is convenient to some extent. So what is this? This is, let me say it for S tau for all, and then the same applies to T tau for all. So these are the C such that S models C and C is universal tau sentence. Okay, and accordingly we define T tau for all And this is let's say, the syntactic way to say this concept, and the semantic way is this one. For all M, which is a tau model, a tau structure, we get that M models T implies there exists an N, which is a superstructure of M according to tau, and then models S. Okay, so if you have a model of T, you can extend it to a tau structure, which is a model of S. And it's clear that if you have two, you get one, because if you take a universal sentence which follows from S, you take a model of T, you take a superstructure with model S, it models the universal sentence, and then it's a substructure of a model of a universal sentence, so it models as well the universal sentence. So is this argument for 2 implies 1 clear? And 1 implies 2 is a basic compactness argument. So what you do, you take the theory S union delta 0 M for M, a model of T. Okay, so delta 0 M is the atomic diagram. So this is equal to the C of A1 AN, such that A1 AN belongs to M, and M models C of A1 AN, and C is quantifier free. Okay? And it's clear that if we get a model of this theory, then this model is a superstructure of M, because it realizes the quantifier free diagram. So this allows to embed the quantifier free diagram into the model of this theory, and it's also a model of S. So it contradicts 2. So if this theory is consistent, if M is a counterexample to the truth of 2, this theory must be inconsistent. Is this okay? Should I move on? Okay, so let me continue the proof. So what happens now is that this theory is inconsistent if M witnesses 2 fails. We get that S union delta 0 M is inconsistent. By compactness, we find C of A0 AN such that S plus C of A0 AN is inconsistent. And now we are in business, because this is a quantifier free formula. So we get that S deduce the negation of C of A0 AN, because S plus C of A0 AN is inconsistent. But now those are elements of M, so they are outside of the language. So we get that S deduce a sentence with the constants which are not appearing in the language of S, which implies that S deduce for all X0 Xn not C of H0 of X0 Xn. Well, and now we also have that M models exist X C of X0 Xn, and this gives that if S for all tau is a subset of T tau for all, which is 1, then we get that for all X not C of X0 Xn belongs to T tau for all, but M models T, and we get the contradiction because it models this sentence, and they're clearly incompatible. Okay, so this is the argument. So we see the fact that every model of a certain theory is embeddable in a model of another theory amounts to an equivalence in the universal fragment of the theory. So if the universal fragment of the theories are the same, every model of one theory embeds in a model of the other theory, and conversely. So this is the first point. And now comes the key notion, which is, I mean, one of those that brought my attention to the notion of model companionship, which is the definition of existentially closed model. Let T be a tau theory. M is TEC if 1 M is a substructure of N, which is a model of T for some N, and 2 is M is sigma 1 elementary in N for all N, which are a substructure of M, and N, which models T. Okay, so it is I mean, this second condition is the relevant one, and the first condition says that it is not trivial. So there is some superstructure of M, which is a model of T, and then such superstructure is a sigma 1 elementary superstructure. Okay. So are you hearing well? Everything is fine, because I have no other way to know if
Everything's
things are going. Okay. So, and now the observation, which is at first time a bit surprising, is that M is TEC if and only if M is T for all tau EC. So it does not depend really on the theory T, it depends just on the universal fragment of T. And why is the case? Well, you take M, you get the superstructure, which is a model, you get N, which models, sorry, let me put it here, T for all tau, and you want to show that it's sigma 1 elementary. Well, since T for all tau is the same universal fragment of T, you can get, by the previous fact, you can get the P, which models T, and is a superstructure of N, because T and T for all tau are have the same universal fragment. And now you apply the definition, and here you get sigma 1 elementarity, which means that if you have a sigma 1 formula with parameters in M, which is true in N, well, the witness in N remains a witness in P of the truth of the quantifier-free formula. And now you use the sigma 1 reflection to get that the witness can be found in M. Okay, and this gives sigma 1. Okay, so you see the notion of T existentially closed depend only on the universal fragment of T. Okay, and another observation is the following. Suppose M is TEC and N is a substructure of M such that N models T, then for any universal sentence, universal tau sentence, we get that we get that M models C if and only if N models C. So you get that when you have a model which is existentially closed and you build a superstructure which is a model of T, well, the fact that it's sigma 1 elementary grants that you are not changing the pi 1 theory. you cannot make a universal sentence true in M false in some superstructure of M, which is a model of T. Does the converse holds? So what I mean by the converse, suppose N models T and M is a substructure, is a superstructure of N such that M is TEC. Does M and then agree on universal sentence? Okay, and the answer is no. You take as N, you take the rational with plus times 0, 1, and you take as M, you take the complex number with plus times 0 and 1. And what happens is that you have that this is a substructure, and you have that this is existentially closed for the theory of fields. So here you get fields, and you get M is fields existentially closed, because in this case one can check that the notion of existentially closed for the theory of fields overlaps with the notion of algebraically closed field. But here you have that there is the square root of -1, which is, you get that this is true. And here you get that this is false. So it's not the case that the two, that if you start from a model of some theory and you build a superstructure which is T existentially closed for the model, for the theory, the superstructure agree with the model on the existential, on the universal or existential sentences. Okay? And well, essentially, this is a peculiar difference between the state of affairs for set theory and the state of affairs for field theory. So in set theory, essentially the examples that I found of existentially closed models for set theory are always preserving the sigma 1, I mean the universal fragment of the model of set theory one starts with to build. Okay. So this is where I found a discrepancy between the standard presentation of model companionship, which I'm going to give right away, and the setup in set theory. There is this non-symmetry. Okay, is everything clear so far? I continue.
Yep.
Yeah, very good.
Okay. So we have that we need another notion, well, let's say notation, which is T tau for all val exist. This is equal to the C, such that T models C, and C is a Boolean combination of universal sentences. Okay, and I use this notation. I don't know. I invented it because I didn't find it in the standard textbooks. Because essentially, if one thinks a moment, one gets that the Boolean combination of universal sentences are essentially of two types: either a universal sentence conjunction an existential sentence, or a universal sentence disjunction an existential sentence. And the interesting case is when you have a disjunction, because that, I mean, the conjunction is more informative, the disjunction is less informative. Okay, so it's important to keep track of the disjunctions that are in the universal fragment rather than of the conjunctions. But that's why I put the val instead of the wedge. And now the key definition, which brings to the notion of absolute model companionship, is the following. Let T be a tau theory. Well, I'll come back to it. Okay, and C a tau sentence. Okay, and we say that C is strongly T consistent if for all R which extends T, we have that C plus R tau for all well exist is consistent. So C is not only consistent with T, but essentially you take a model of T and then you can expand this model to become a model of the universal fragment of the theory of the model you started with and C. That's what this definition says. So it's not only consistent with T. You take any completion of T and C is consistent. Well, maybe the completion as the negation of C among its truths, but this can occur only if C is quite complicated, not if C is a universal or a Boolean combination of universal sentences. In that case, C has to be consistent. And in general, if you have a complicated formula, and we will focus on pi2 sentences, we will have that a pi2 sentence is strongly T-consistent, essentially, if you can realize it in some some structure which satisfies exactly the same universal sentences that are realized in some model of T. Okay, so is this definition clear? Because that's essentially a key definition of this talk. Okay, and here is the first another basic fact about strongly T-consistent pi2 sentences. Fact: assume C is pi2 sentence for tau, which is strongly T-consistent, then let M be a TEC model, then M models C. Okay, proof. So what happens is we start with M. Okay, so it's a TEC model. So and we get to a model of N, which is a model of T. Okay, and actually here we have sigma 1 elementarity, and now we let R equals the theory of N, and we get that R is also, then we get that R tau for all well exist is realized in M, because here you have sigma 1 elementarity, so every Boolean combination of universal sentences which is true in N is also true in M. And now we plug in the fact that C is strongly T-consistent. This means that there exists a P, which is a model of C plus R tau for all well exist. But now we observe that this theory is exactly the if we take of this theory the Boolean combination of universal fragment, well, we don't add anything with respect to this. Okay, because this was already complete in essence. Every pi1 sentence or Boolean combination of pi1 sentence is decided because the theory of N is a complete theory. So we get that those two are equal, which means by the previous fact that there is a superstructure P star, which is a model of C plus R tau for all well exist. but this is a super theory of T for all, which means that M is now a sigma 1 elementarity. M is sigma 1 elementary in P star. We have a pi2 sentence which is true in P star. We can reflect it to M because we take, so we get C is for all X exists Y, C X Y. We pick A belonging to M. Then we get that P star models exist Y, C, A, Y, and then we get that M models exist Y, C, A, Y, because we have sigma 1 elementarity. Since we can do this for every element in M, we get the reflection. Okay, so we see that every pi2 sentence which is strongly T consistent is going to be realized in the T existentially closed models. Okay, is this clear, this part? Can I move on, or there are questions? Okay. So the question is are the TEC tau models axiomatized by the strongly T consistent pi2 sentences? Okay, and again, the answer is no. No, counterexample. Again, the counterexample is always the same, rational against algebraically closed fields. So we take as C, we get exist X, X times X plus 1 equals 0. This is C is not strongly fields consistent because it fails in the rationals. But ACF models C. C is true in every algebraically closed fields, and one can check that algebraically closed fields are exactly the existentially closed models for the theory of fields. Okay. Okay, so here is the where we start from to depart from the standard theory of model companionship. So let me now define model companionship. So let TS be tau theories. So T is the model companion of S. If 1 T tau for all is equal to S tau for all, so I'm just working with the universal sentence. T is model complete. I have not defined this notion, and I'm now giving a definition. T is model complete means T, for me, this is the definition I give. It's not the standard one, but it's axiomatized by the T for all EC, by the pi2 sentences true in the T for all EC models. or actually it's the same T for all well-exist EC models. Okay, it can be checked that in this specific case we can, or equivalently TEC models. Okay, because the universal fragment of these three theories are the same. The universal fragment of T is the same as the universal fragment of T for all will exist, and is the same as the universal fragment. Okay. So this is the notion of model companionship, and standard example. Algebraically closed fields are the model companion of fields. They satisfy exactly the same universal sentences. They do not satisfy the same existential sentences. So there is the square root of -1 is a witness of an existential sentence which is true in an algebraically closed field, but not in the rationals, which is a field. Okay. Okay, and now I want to tweak a bit this definition. And okay. And I get the definition of absolute model companion. Let TS be tau theories. T is the AMC of S. So let me use this abbreviation, which means absolute model companion. If 1 T for all well exist tau is equal to S for all well exist tau, and 2 T is model complete. Okay. So, and now you see, for example, ACF is not the AMC of fields. Why? Because the sentence exists x squared plus 1 equals 1 is an axiom of ACF, actually in the universal, in the Boolean combination of universal sentence axiom of ACF, but it's not an axiom of the theory of fields because it fails in the rationals. Okay, so this equality is false. This second part is okay, but this first part is false. Okay, and what happens is that for what I'm aware of, in set theory, we have plenty of model companionship results for set theory, but those model companionship results are of this type, not of the weaker type with for all in the place of this. Okay, so this is why I get to this definition.
Yeah, one quick question. Is point 1 strictly stronger than just saying that the existential and the universal part are the same?
Yes.
Okay.
Yes. So not just the universal sentences, but also the Boolean combination of universal sentences. So the existential sentences are the same, and also the disjunction of a universal and existential are the same.
Okay, thanks.
One
So
more question.
I continue.
One more question.
Yes.
Can you say what the usual definition of model complete is?
Yes. T is model complete. There are many definitions. If for all M substructure of N, which are both models of T, we get that M is elementary in N. So this is the standard definition. And here you can put elementary or sigma 1. It's the same.
Okay, thanks.
Okay, and another definition, well, no, I will come back to that later on. Okay, okay, I move on. Okay, and okay, so you see we have this equality which replaces the equality for all, and this suggests that there should be some counterpart on the semantic side. So what does this amount to, this equality amount to, say, at the level of bi-embeddability of models of T with models of S? And this is the equivalent proposition. Let TS be tau theories. The following are equivalent. 1, T tau for all val exist is equal to S tau for all val exist. And 2, for all, inclusion. Sorry, for all M, which is a model of T, there exists an N, which is a substructure of M, and N is a model of S, and M and agree on universal sentences. So you are in the setup where you cannot, when you build the superstructure of M, which is a model of S, you are not forced to make false some universal sentence that was true in M. You can do the model of S while preserving all the universal sentences that were true in M. So that's the equivalent of this syntactic property. Okay. I move on. How much time am I supposed to have? 1 hour or...
I'm actually not sure. Let me check and get back to you.
Okay. Okay, and let me just give an example of AMC. So we take the theory. S is the theory of Z, sorry, Z with the order, and T is the theory of rationals with the orders. Those theories are complete, and it's easy to see that Z embeds into, that a model of S embeds into a model of T, which embeds into a model of S, and so on and so forth. What you do, you have a model of S, so it's a discrete linear order. You blow every point to Q, and you get a model of T. And here you have a dense linear order, and you blow every point to a copy of Z, and you get a model of S. And in this way, you pass from one to the other. And since you are considering complete theories, you are not changing the universal sentences that are true in those models. They are always the same. But you get that this theory admits quantifier elimination. And then the standard definition of model completeness is satisfied, because if both are models of T, well, if you have a substructure relation, since you have quantifier elimination, this amounts to, say, elementary substructure relation. So this is model complete. Those two theories agree on the Boolean combination of universal sentences. So this is the absolute model companion of S. Okay. And now we will, later on, we will see many examples from set theory.
So Matteo, you probably can't see the chat, but you have another 45 minutes.
Okay, perfect. Then I will be on track to say everything I wanted to say. Okay, and here is the characterization that brings my attention to this notion of AMC. Let TS be tau theories. And the following are equivalent. 1, T is the AMC of S, and 2, T is axiomatized by pi2 sentences which are strongly S consistent and is model complete. Okay, so the strongly S consistent pi2 sentence gives the axiomatization of the absolute model companion of S when it exists. The point is that the existence of absolute model companion or of a model companion is a absolutely non-trivial property. So in general, you should not expect that the theory has it. Okay.
So this axiomatization condition, this is a replacement of the first part of the definition of AMC.
Yes, exactly. Okay. So, well, actually, it's a replacement of, I mean, one definition is, you see, that's the other definition. Sorry, here. Okay, so, so 2 is reinforcing, so 2, in the case of model companionship, you just have the request that you have model completeness. And essentially, the point is, we know that these pi2 sentences are true in the existentially closed models, but are there some other sentences which are true in the existentially closed models and are not strongly as consistent? This is what happens in the case of algebraically closed fields versus fields. And this 2 is saying, no, you are capturing everything.
Okay, thanks.
Okay, and now comes the second model theoretic ingredient of this analysis of, I mean, to analyze set theory, which is partial moralization. So what is the problem with model companionship? The problem with model companionship is that it is very sensitive to the signature. You can have the same theory, you axiomatize it using a signature, it has a model companion. You axiomatize it using another signature, it does not have a model companion in the new signature. Okay, and this is in contrast with the standard tameness properties. For example, stability of a theory T is independent of the axiom system you choose to formalize T. The same for the not independence property, the same for minimality. Okay, so let me start with the problem we have. Okay, so let tau be the signature for fields, so plus time 0, 1. The T be algebraically closed fields, and S be fields. And sorry, S be commutative rings. Sorry, so it's easier for me to build a counterexample with no zero divisors. Okay, and now we consider C, which is a model of T, and then it is a substructure according to tau of Cx, which is a model of S. Okay, and actually you get that it's sigma 1 elementary. So if you take a polynomial here where the coefficients are really complex numbers, then the solution of the polynomial that you find here, you already found in the complex number. Okay, so that's what sigma 1 elementarity amounts to say, essentially. But now we do some complication. So what we do, we pass to tau prime, which is plus times 0, 1, and we add the multiplicative inverse. Okay, and now we have to interpret the multiplicative inverse. Well, here we know what to do. We take the multiplicative inverse. Here we have a problem because not all polynomials have an inverse, essentially just when they are constant polynomials, but we have a very easy solution. So we add this axiom. So we get the axiom that says for all x, if there exists a y such that x times y equals 1, then we get that x times x minus 1 equals 1. Or no, there is no y such that x times y equals 1, in which case x minus 1 is 0. Okay? And what happens is that this axiom serves the purpose of defining the multiplicative inverse as we want here and here. So here it's really, this axiom is satisfied and the interpretation is the multiplicative inverse. And here this axiom is satisfied. Whenever you take a complex number, the inverse is the complex inverse. But when you take a polynomial which is of degree bigger than 0, then the inverse is the 0 polynomial. Okay? So what happens is that here you get that tau prime is also true. So with respect to this expanded signature, so now we have also the -1 symbol, the tau prime substructure relation holds true, but this is false because here you get exist x times x minus 1 equals 0 and x is not 0. And here we get the converse. Okay, so we get a sigma 1 sentence, which is true in this bigger structure and does not reflect here. Okay, so we changed the signature, and with the old signature, everything was fine. The algebraically closed field were the the existentially closed models of the theory of fields. We expanded the signature, and the algebraically closed fields are not anymore the existentially closed models of the theory of commute. Well, they were also, the point is that the algebraically closed fields were also the existentially closed models for the theory of commutative rings with not zero divisors. I mean, we should be easily aware of this fact, but we expanded the signature. We had the symbol for multiplicative inverse. We maintained the substructure relation. We destroyed the sigma 1 elementarity relation. Okay, so what it says, this result, is that if we consider this theory in this signature and this theory in this signature, then we get that this is the model companion of this. Then we consider this theory in this signature, this theory in this signature, and this is not anymore the model companion of this. Okay, so we changed the signature and we broke the model companionship relation between the theories. So what we do is, okay, so let's attach to a theory the signatures for which it admits a model companion. Okay, and to do this, we proceed as follows. So we have a signature, and we take phi x. So is this counterexample clear?
Yes.
So we have phi x and psi x y tau formula, and we consider two types of axiom. The first type of axiom is saying, okay, I'm considering this formula phi x as a quantifier-free formula. How do I do this? Well, you can imagine we do this. Phi x is equivalent to R phi x. Okay, so we add in tau union R phi. So we add a relation symbol of the correctarity and we predicate that whenever we have the formula phi true, we also have the atomic formula R phi true. And then we also do partial scolemization, and this is what we use the formula psi for. So what we do is for all x, if there exists just one y such that psi x y, and then we say that f c of x equals y, or it's not the case that there exists one y such that psi x y, in which case we set that fc of x is some constant c tau, and this is in signature tau union fc and c tau. So essentially the problem is tau may not have constant symbols, so we add one constant symbol which we use for the trash value, so when we don't have a unique witness, and then we use the existence of a unique witness to define the function symbol, and if there is no unique witness, then we let the function symbol be evaluated trivially. Okay, so this is exactly, so this is what we did when we expanded the signature with the multiplicative inverse. So the multiplicative inverse is unique. So in case we have a unique multiplicative inverse, we are in this situation, and we let the interpretation of the function symbol be the multiplicative inverse. Or if there is no multiplicative inverse, or there are possibly more than one, well, which is not the case in this situation, then we let the multiplicative inverse be interpreted by 0. Okay. So this is what we applied in the case of, in the example of the previous slide, of the previous page. Okay. Is this clear? So the standard modelization process that one finds in the courses is you add the relation symbol for all formulae. And I am slightly more liberal because it's convenient. I add also function symbols, but I'm very picky. I want just one witness. This condition is important because otherwise the interpretation of the function symbol appeals to the axiom of choice if we just know that there is a witness. But if there are too many witnesses in too many occasions, then I have to use the axiom of choice to interpret this function symbol, and I don't want. Because the point is that with this stuff, if I have a model of, if I have a tau structure, I have a unique possibility to extend this tau structure in order to become an axiom of, to become a structure which realizes those axioms. Okay, there is no chances. I have freedom just to interpret this constant symbol, but once the constant symbol is interpreted, those axioms tells me how all the other symbols must be interpreted. While if this condition is dropped, then I may have many different interpretation of this Skolem function, which are compatible with the fact that it's a Skolem symbol for the formula. Okay, so fact, if M is a tau structure, there exists just and C belongs to M. There exists a unique expansion of M to tau union FC R phi, such that expansion N, such that N models X 0 phi plus X 1 C plus C is interpreted plus N models C tau equals C. Okay, so the unique freedom I have is to decide what is the value of this constant, but once I decide the value, then the rest is fixed. So this allows me to define unambiguously the for A contained in formula of tau times 2, let T tau A equal X I C, such that Ci belongs to A, and this is giving me a partial modernization of a theory. So T plus T tau A is the partial modernization of T induced by A. Is everything okay? I just turn on the light.
Yes, I assume you'll tell us that this is good for something.
What?
I assume you'll tell us that this is good for something.
This is?
Useful.
Yes, I'm going to, very soon you will see it's very useful. Sorry, for the moment it's just loading a lot of information on you and you don't see where I'm heading, but I will soon come to the point. Okay, so let me just say standard modernization is of T is T plus T tau A for A equal form tau times 0. This is what one learns in order to eliminate quantifiers and maintain the theory. Okay? And now here is the invariant that I'm attaching to a theory. Definition, let T be a tau theory. And we let spec AMC of T is equal to A contained in form tau times 2, such that T plus T tau A has an absolute model companion. And I can define accordingly spec MC of T. Okay. So the idea is how am I going to detect the property of a theory? Well, I look at the subset of the formulae for which when I'm declaring that those concepts are simple, so I equate them to atomic formulae or to Skolem functions, then I'm making the theory simple in the sense that it admits a model companion or an absolute model companion. Okay, so this is a complicated invariant because potentially you get 2 to the LF0 many sub. I mean, if you have a countable theory, then you get possibly you are attaching a subset of the real. Sorry, a subset of the real. You can have possibly 2 to the LF0 many A in the spectrum. Okay, but the point is that when you detect that an A is in the spectrum, you are getting important information on the theory. Essentially, the idea is that when you get that an A is in the spectrum, you are detecting concepts which are central for the theory. The formula that are in A are detecting fundamental concepts of the theory. And I will show you soon examples. So for the moment, what happens is that I can show that this invariant is useful when T is set theory. I don't know if this invariant is useful in other contexts, but I suspect that it should be. I mean, it's just more complicated to handle that simplicity need or something. But the point is that it's an invariant that it's meaningful for an arbitrary theory. So you don't have to first show that the theory is simple and then simple in the sense of simplicity, tameness, or whatever, stability, and then you can analyze the theory once you know that it has a nice tameness property. This stuff can be done for any theory. In particular, accordingly to model theorists, set theory is not tame, it's very bad, but this is a very useful classification tool for set theory. Okay. Is it clear so far? Because now I'm going to state the theorems for set theory. Okay, so for example, one can check that empty set belongs to the spec of model companion of fields in signature tau, fields for tau equals plus times 0, 1. While one can check that spec, I'm not going to prove it, but one can check that the spec of AMC fields is equal to empty set. So there is nothing for tau equals plus times 0, 1. Okay? So here is actually here it's something like this. Well, no, and it's not entirely correct, but essentially modulo small perturbation, this is the unique element in the spectrum of fields for model companionship spectrum. Okay.
This example is illustrating some kind of fundamental difference between model theorists and set theorists or something like this.
In which way?
It seems maybe a model theorist wouldn't consider this absolute model companion, for example.
Well, I mean, there are very basic examples which are absolute model companions, but are not model companions. The point is, I was really surprised not to find this notion of absolute model companionship in any of the standard model theory textbooks. And when I asked to model theorists if they knew this notion, nobody told me that they knew it. So apparently, it's a new notion. Okay.
The second example seems to suggest it's a question that they wouldn't ask.
Yeah, maybe. Yeah. So now the point is AMC spectrum of set theory. Okay, so the first observation is that epsilon is not the right signature for set theory. I mean, it's good for axiomatizing, but it's not good to detect the basic concepts of set theory. The basic concepts are expressed by epsilon delta 0. What is epsilon delta 0 is R phi delta 0 formula union G1 G10 GI Gödel operation as in YAC, and you also add empty set and omega. And I leave you as a very basic exercise to check that this is actually let's say obtained by I mean, these are expressible by the graph of this function are expressible by delta 0 formula, and you need just a fragment of ZF to prove that those are total functions with well-defined. Okay, and to define empty set and omega, you can do that with the delta 0 formula. They are the unique solution of the delta 0 formula. Okay, why am I saying this? Consider try to formalize x, y equals z in epsilon signature. I'm not going to do this because I would take a full line and it would take me 1 minute to write down the formula. But in this signature that I'm writing here, that's it. I have a function symbol for the pair, for the order pair, and I can write this like this. So in epsilon signature, the standard axiomatization using Kuratowski trick gives a sigma 2 formula. And then if you want to define functions using order pair or binary relation using order pair, then you grow up in complexity. So already to say that something is a function, you need something like a sigma 5 or sigma 6 formula, which is not right and completely unreadable. So already writing this is unreadable. If I write the formula here, you won't recognize that it's axiomatizing that Z is the order pair of X and Y. Okay. Let me add this notation. Epsilon A is equal to R phi FC, such that phi 0 belongs to A and phi 1 belongs to A. And ZFC delta 0, well, then one can check that epsilon delta 0 is equal to epsilon A for some A contained in form epsilon times 2, and ZFC delta 0 is equal to ZFC plus T epsilon A. Okay, so we are enriching ZFC with the axiom that says that delta 0 formulas have to be interpreted the correct way. Okay, and now what happens that, for example, CH, X is Aleph 1 is pi 1, well, sigma 1, well, is in ZFC. Well, actually, ZFC delta minus delta 0 for all val exist in epsilon delta 0. Why? Well, you can check what does it mean that X is Aleph 1. It means for all F is a function, the domain of F belongs to X, implies a range of F is different from X. So this is saying that X is a cardinal. Sorry, I have to add that X is an ordinal. So it's a linear order. Epsilon relation makes it a linear order and is transitive. And I have to add there exists an F dom F is equal to X times omega, and for all alpha belonging to X, F restriction to alpha times omega is a surjection on omega. And you can check that this piece is delta 0, this piece is delta 0, this piece is delta 0, and the unique solution of this formula is the cardinal Aleph 1 in any model of a sufficient fragment of ZFC. Okay, so this part is pi 1, and then this part is sigma 1. So it's pi 1 wedge sigma 1. Okay. And similarly, you can check that X is Aleph 2 is pi 1 wedge sigma 1. And so you can say CH, what is CH? Is exist X, X is Aleph 1, and for all, exist F, dom F equals Aleph 1, and for all R is a subset of omega, implies R belongs to the range of F. So there is a surjection of Aleph 1 onto the reals. You see, this is sigma 2, and this is sigma 2. So CH is sigma 2. Not CH is actually sigma 2 wedge pi 2, because this piece you need in order to state that there exists a F1, and the second piece you have to negate. So this becomes pi 2, and this becomes sigma 2. Okay. So you see now in this signature, the standard concepts get the right complexity. And this is what we are used to. Essentially, we just don't care to make it explicit. Saying what is the signature in which we are axiomatizing them. We say that we are axiomatizing in the epsilon signature, but we regard the delta zero formula and the Gödel operation as saying basic facts. Okay. Is this clear? Okay, so let me move on, and I can now start to state the results about set theory with this model companionship. Okay, so assume tau extends epsilon delta 0 and T extends ZFC tau. What is it? It's ZFC delta 0 plus replacement for tau formula. Okay, let M be TEC. Okay, we take a model of which is a tau structure which is T existentially closed. Then is it a strange structure? No, it is a model of ZFC tau minus. So it is a model of everything except the power set axiom. Okay. Furthermore, assume tau contains epsilon delta 0 union kappa and H kappa plus M tau M. By this I mean the interpretation of tau in H kappa plus is always a substructure of M for M, a model of ZFC tau. Then for all X, there exists an F, dom F equals kappa, wedge, run F equals X, belongs to, well, is strongly ZFC tau consistent. In particular, M models models this formula. Let's say C. M models C if M is ZFC tau EC. Okay. So what happens is that what kind of theory are the existentially closed model for set theory outlining, bringing out? They are bringing out the theory of H kappa plus. Okay. So if you have a constant, for example, if you have a constant for omega 1, it's not hard to check that H aleph 2 is always sigma 1 elementary in V in this signature, epsilon delta 0 union constant for omega 1. And then it means that if you take a existentially closed model for set theory in this signature, then this existentially closed model is a model of ZFC minus plus every set has size at most aleph 1. So the ZFC existentially closed model in any signature that is expanding epsilon delta 0 are describing a theory of H kappa plus for an appropriate cardinal kappa. Okay. So this is the first thing is when I'm looking at the existentially closed model for set theory, provided I'm going to a signature which is meaningful, so an expansion of this signature, then I'm getting the existentially closed models are describing a potential theory of H kappa plus. Okay. And now comes the main result. No, first, is it void of content, the AMC spectrum of set theory? No, there are many. So let T contains ZFC, be an epsilon theory. Then for any kappa such that T deduce exist in, let's say, exist in solo just one x phi kappa x, and for all x phi kappa x implies x is a cardinal. So kappa is a definable cardinal. So this is the meaning of this stuff. There is a unique solution of this formula, and the solution of this formula are cardinals. Then you get that there exists a kappa contained in form epsilon times 2, such that a kappa is in the spectrum, actually in the AMC spectrum of T, and let's say the AMC of T with respect to this expanded signature as models ZFC minus plus for all x, there exists f, dom f equal kappa, and run f equals x. So we get that there are many, for any definable cardinal kappa, I can cook up a signature such that the absolute model companionship of set theory with respect to that signature exists and is describing the theory of H kappa plus. So kappa could be omega 1, omega 2, omega 3, aleph omega, first super compact, first inaccessible. Okay. So this is saying the AMC of set theory, the spectrum with respect to absolute model companionship is very rich. Okay, and now the stuff about CH and forcing axioms. So theorem, assume T expands GFC and is epsilon theory, and A belongs to the spectrum with respect to here it's important that it's a spectrum with respect to the absolute model companion and not the model companion. It is such that epsilon A contains epsilon delta 0, and ZFC plus T epsilon A contains ZFC delta 0. So I'm interpreting stuff correctly. Then we have the following. If T plus not CH is consistent, CH cannot be in the absolute model companionship of T with respect to signature A. And second, the same applies for T plus 2 to the aleph 0 bigger than aleph 2, consistent, then 2 to the aleph 0 bigger than aleph 2. Not in AMC. Okay, consistent. Okay, well, here the sum curve. I mean, here it's really just the non-CH as I stated it. Here I have to be more careful, but essentially it is this stuff. So what happens is you can never put in the absolute model companion of some theory which extends CFC and has not yet committed on the value of CH. You cannot put CH in the absolute model companion. Okay, nor you can put 2 to the aleph 0 bigger than aleph 2. So it remains open whether you can put 2 to the LF0 equals LF2. And this is the other theorem. There exists a B contained in form epsilon times 2, such that for all T extending ZFC plus there exists class many supercompact. Actually, weaker assumptions are needed. Well, we have that 1, B belongs to the spectrum of T. 2, a definable version of 2 to the LF0 equals LF2 belongs to this spectrum. And 3, AMC of T with respect to this signature given by B describes the theory of H LF2 in models of MM++. Okay, and also it's we also have that T for all well exist epsilon B is forcing invariant. You cannot change the universal fragment of set theory as axiomatized in this signature using forcing. You can change the pi2 sentences, but not the pi1 sentence. And note that 1 holds for any T which extends the FC plus large cardinal. So for example, you can extend T with CH. So T satisfies CH, but in the absolute model companionship spectrum, you are getting a theory of H LF2, which satisfies 2 to the LF0 equals LF2. T could satisfy 2 to the LF0 bigger than LF2, but in the absolute model companionship spectrum of this B, you will get 2 to the LF0 equals LF2. Okay? So here the result is saying, even if you have a theory which decides CH, you are forced to put 2 to the LF0 equals LF2 in the spectrum of this theory, while you are not forced to do it when the theory is not deciding CH. Well, you cannot put CH nor 2 to the LF0 bigger than LF2 when the theory has not decided the value of the continuum. Okay, and I think I can stop here because I mean there are parts of these results that are quite trivial to prove, but I think I'm already taking much of your questions, so I stop here.
All right. Are there questions? I guess I have one. So this point number 3 in this theorem, can you say a little bit more what describes means?
Yes, I can say what is the exactly. So this is equal to the C, such that C is pi2 for epsilon B, and T forces that C relativized to H LF2 is forcible. Sorry, T models that. So this is one possible description, but you can have another, which is C such that there exists M, such that M models T plus MM plus C H LF2. Sorry, T models T plus yes, plus C H LF2.
Okay, so some kind of maximal theory of.
Yes,
of
Yes.
HL.
So essentially, the point is this theory is described by forcibility. So if you have a pi2 sentence which is forcible to hold in HLF2, then this pi2 sentence is going to be true. And here I have to specify that epsilon b contains epsilon delta 0, and it has a constant for omega 1, and it has a predicate symbol for the non-stationary ideal.
Mhm.
And then it has a predicate symbol for the universally paired sets. Universally paired. A certain universally paired sets.
These would be natural things in the context that you're.
Yes.
I mean, to even describe MM double plus, you need these things, right? For example,
What?
to describe something like MM double plus, these are kinds of concepts that you need.
Yes. Yes. Exactly. To describe what happens in the theory of HLF2 in models of MM. Well, not even in models of MM++. I mean, to describe the theory of HLF2, you better have the non-stationary ideal as a predicate. You better have omega 1 as a constant. And maybe you want to use some universally paired sets as well.
Right. Are there other questions? All right. If not, let's thank Matteo for a really nice talk.
The paper presentation was awesome.
Thank